Hi, Sachin.
Hey,
Hi, Martin.
hi, how are you?
Yeah, not too bad, not too bad. What about you?
Pretty good. I'm glad you joined. It looked for a while like it would be an all Apollo meeting. yeah,
I
I
would
was
have
worried about
loved to watch the recording of this.
that.
And of course, Kamil is also here. Uh,
Ah, great.
he's not in the attendee list yet. Yeah, Michael will join also, but I believe he's on the road. Check.
Hello. Hi guys.
Hello. Hey, I think Shane has a PR to remove himself from the list, but it hasn't auto merged. Maybe that's just how the auto merging rules work.
Fine.
Oh, it might only auto merge once. Yeah, I think it only auto merges if you add a line, and if you try to modify or remove lines, it doesn't auto merge. I think.
Mm.
But, yeah.
I think I can. Yeah, I can.
Or as the repo permissions can like presumably approve or whatever.
He's, he's gone.
Well, I might actually have permissions. Let me.
It's done.
Oh, great.
Or it should be at least. Yo. What happened now? Is Derek missing? Kamal, can you add yourself?
I did, just did. That's why I'm like, not talking.
You concentrated in doing a pull request.
Yeah, I have like too many windows open.
Interesting discussions ahead. So Kamal is in. Now you're allowed to talk. You're in the list. Now you have permission to talk as well. That would be a funny thing if we would just allow people to join, but they're forced to be mute. They're not in the list.
Yep.
Okay, so Derek is here as well. Yeah.
Should
Um,
we wait for Michael or do you
I
want to?
think we can probably just start. If he wants to see what happened in the beginning, then he will be. He can either read the AI summary or he can watch the video. Okay, so by being here, we all agree to the membership agreement and the participation and contribution guidelines and the code of conduct, as always. And here he is. And then we can start with a round of introduction in the order of the attendees.
I think this is the first time I'm on first. um, I'm Martin and I'm with Apollo.
The chin from Apollo.
Derek here, also from Apollo.
I'm Pascal from Chili Cream.
And Camille from the guild.
And Michael, if you could add yourself to the agenda, that would be great.
Yeah, we just discussed we may not actually allow people to talk unless they've added themselves to the lists.
You're muted, by the way, or you have the wrong output device, input device.
Yes,
Maybe
I have the wrong output device.
one of the it could also be. Okay, cool. So we only have one topic, again, very generously added with 15 minutes. Does anyone has something else which is burning? Then we could do this first because the satisfiability discussion will probably again take the whole meeting. I actually thought about adding it as 1 minute, but I thought 15 is fair enough. Anyone? Okay, then let's do a quick recap. By the way, do you see my screen?
Yes. I do.
It's weird because I don't see that you see my screen. It makes me nervous. Um, Okay, so let's see. We have this. Let's move this out quickly. And then let's move.
Yeah, by the way, just one additional info from this meeting on. We have AI summaries on. Just that you know that AI is
Listening.
writing a summary. Yeah.
Yeah.
Okay, cool. Very good. Now I also see that I'm sharing or what I'm sharing. So just as a quick recap about what we have discussed last time, I think the main gist of the meeting last time was that satisfiability is going to be a very complicated topic, and we try to simplify it in the spec a bit. So there's no optimizations, even though you probably need optimizations in the actual implementations. So we can revisit all the paths multiple times. We don't have to worry about complexity too much. And one input of Martin last week was that the satisfiability could essentially be a two-step phase, where in the first step we generate all the possible path, a path being something like I don't know, do we prefix it with query? You do, right? The path.
Yeah, you always start from a root type.
Yeah, so a path could be a path through the graphical schema to a leaf field, and the leaf field here would be D. And once we have generated all possible paths, we essentially go into the second step of satisfiability. And the second step of satisfiability is very easy. Essentially, it is that all these paths must be executable for the schema to be satisfiable. Yes, Sachin?
That doesn't quite work as written is the thing, right? So like there are infinite paths is the thing. And to be able to determine whether you've reached a loop, you basically have to be executing while you're sort of listing paths. So you can't necessarily just save the step of checking whether it's satisfied or whether you actually can make the query till later, because you need it so you can not generate an infinite number of paths from the start.
Yes, that was the thing about loop detection, and the input in at the end of the meeting from Martin was that maybe the generating of the paths and the execution is not a step one, step two, but more like we use the execution to generate the next paths we have to visit, something like this.
Or determine when we stop
Or determine when to
like
stop.
extending the path. Yeah.
So I think what would be really helpful is this whole loop detection thing is something that I believe once you have a shared understanding what is a loop and how this exactly works with simple examples, then we can see from there where this fits in the best. You did you explained it last time, Sachin, but maybe we can work on some examples where we actually see the possible. You explained it last time, like you know that you're in a loop when, and now it's your turn.
Yeah. So yeah, I can talk more then. So the gist is as we're going along and sort of creating these paths, you can think of as a well, you can think basically you're sort of starting out from the root and you're sort of exploring this space of paths, right? And along the way, essentially, you have this notion of an open path, which is a path that doesn't end in a leaf field, right? So like while you're doing this, you can imagine that for an open path, um, you can imagine across all the possible ways you can satisfy that path through queries the subgraphs, you can imagine that after at the end of all those, you can imagine a set of possible subgraph comma type pairs you could be at by the end of that, if that makes sense, right? So like it's possible in this case for ABC, for example, that maybe after that point, and if you look at query planning and what it would tell you, it might be that at the end of that you could be, let's suppose C's return type is like capital C, right, or something like that. Let's say. So like it's possible that the end of, if you look at your query planning and it comes back and it tells you that you could be in subgraph 1 with type C, or you could be back in subgraph 2 with type C, but not subgraph 3 or 4 or 5 or something like that, right? And in that sense, that's sort of the state that you get back from that you need to keep track of is those pairs of subgraph comma type and which ones are would you possibly be at that point in time.
So it's a set of combinations of subgraph and type at a certain
for a
certain
certain open path.
That's right.
the A, B, C.
Yeah.
Okay. So that's what you need to keep track of. Right?
Yeah, in reality, I think it's even maybe just comma subgraphs at that point too, because the type should always be the same. So you could, align it a bit there.
True. True.
Technically, yeah.
One question.
Yeah.
I added myself to the agenda, so I guess I can speak.
Allowed to speak now.
What I wanted to ask is like, I guess, like, I don't know, I wasn't at the last meeting, so I'm not like entirely sure what was discussed, but like the whole thing with the satisfiability, I believe the easiest path to get there is to have like a graph. So, when you have nodes and edges and so on, and possibly even like two representation. One is for the public API, and then the other one is like contains all the details about the subgraphs and so on, or like provided paths, requirements. I mean, requirements, it's not really, but like, so what I was thinking is like, if the algorithm could say like, oh, it's a graph, you have to navigate through all the, possibilities, let's say, and you keep track of all the possible, variants, like all the possible paths that were, like, for example, if you go from a query to, let's say a query is a node, and then, I don't know, users is a field, right? And that becomes an edge. And then you go deeper and deeper and deeper. And so while you do this navigation on the, like, I don't know, public graph or like public schema, you check if the underlying, I don't know, graph has an option to get there. And this option is actually like you can decide if it's like depth first, breadth first, whatever. So that would be like, people know the graph. So like explaining the algorithm for a depth first and so on would be like easy, I guess. Then the only thing really that is like custom from like graph traversal is the checking of requirements. So I don't know, maybe this would be simpler because like I don't see like
I think that's
right.
basically what we're trying to do here.
Yeah, but what I mean, like there's the generate all possible paths, right? And then this actually, like, does it mean you generate all possible paths for all the fields at the first step? Because if
No. That was actually the thing that that Pascal just mentioned that we discussed at the end last time. So basically, what we're doing is we're specifying a graph traversal algorithm that sort of generates all the paths by walking it. But in the process of doing that, we actually need to decide when to stop to avoid loops, because without it, I mean, the graph is basically infinite.
Yeah,
Because it's not a directed or
So the base. So what we're trying to find out is essentially the key. The key, I believe also the key probably of optimization in the end is to when you start caching is the same knowledge, right? You need to have a path and a certain state, and if you already know that this is good, then you can skip it. And
yeah, and I think that was what Sachin was trying to explain, but he hasn't gotten to the second part yet.
Right. So the idea behind loop detection basically is you're keeping track of, like, you can imagine that a state that sort of keeps track of like the potential options you could have going forward for query planning that encapsulates that state. And that's kind of what we're keeping track of with this sort of subgraph stuff is like, you can imagine that if you wanted to query plan from this particular point in time, there's certain information you need to remember. You don't necessarily remember the path used to get here. At least in common federation, not common federation. In a simplified version of federation, you don't technically need to know the entire path used to get here. You just need to know the subgraph and the type you're on. For each one, if that makes sense, right? You don't necessarily need to know the rest of the path you use to get to this point. So that's why the state doesn't include path information. That's why we only really include like a list of subgraphs there. There's another slight simplification here we're doing around provide. This is maybe I don't know, maybe I'm more in the weeds.
Yeah, I would leave that out, but
Yeah.
I think the condition that you described last week was when the number of options doesn't grow.
Yeah. So you can think of like the set of subgraphs potentially could get smaller as you revisit the node, right? Because it turns out that it turns out that maybe it's from one. If you keep going along with just that subgraph comma type, and you keep trying to query plan for just that particular type, it turns out you can't actually reach back. There's some issues with that particular possibility, right? And so it ends up being smaller. So in that case, you still have to keep going. You can't say you've stopped at that point. It's only when basically when you visited the node previously and the number of subgraphs, or not the number really, when the set of subgraphs is a superset of the one that you're at, that's when you can stop. Sorry, it's the other way around. When you've reached a point when the set of subgraphs is a superset potentially equal to a previous visit's set of subgraphs, that's when you can stop.
When it
So like if you can imagine like whenever you visit a node,
so to make it it's set, if it's a subset, you cannot stop.
that's right.
It's
It'll be a strict
if the
subset.
options are constant, or
Now,
actually.
they can apparently also grow. That's fine as well.
Yeah.
Because it
It,
could
it,
be that you have more possibilities now based on the
Yeah.
context that you're in. As long as
Exactly.
they don't shrink, that's what Sachin explained last week, is if it's a subset, you have to continue until you
well,
until you
it,
have
it
passed that, right?
It doesn't really just necessarily just a subset. It's just that basically if there is a previous visit that exists and that previous visit has a subset of subgraphs of the set of options you have now at this current visit, then you can stop. And all other cases you'll have to keep going. And then in that subset, the subset is not a strict subset. It's just like a equal or a subset. Because there's also possibilities where technically they're not over like subset or superset. They actually could be like off by a bit. So there's like I guess that's why we don't want to phrase it as the inverse, if that makes sense. Um,
So when the list of subgraph is the same or bigger.
when you visit a node already and the list of subgraphs is the same as a previous visit, or the list of subgraphs is a superset of a previous visit, that's when you can stop.
Okay. If the list is empty, it's then you're in trouble, right?
Right. Then you're in trouble. If at any point you reach a point where you have no options to get somewhere, that's basically saying that you could not satisfy that query because you have no way of moving forward. Um, so any field you try to take next will not be able to be planned, basically.
Yeah. And maybe we should refer to that list as a list of options just for the algorithm, just to make it clear sort of what we're describing here. If that's sort of wording that people find helpful.
Yeah, so list of options.
Yeah, and then we define for now like an option as basically a subgraph, but there might be other state in there that we need at a later point for other features.
Yeah, it very much depends on the federation feature that you implement as to what the state looks like. Our state does not
Yeah.
look like this today in the current algorithm in federation. That's because we have
We,
certain
we have context, right?
yeah, we have context keys as well there. Um,
Yeah, I mean, this is with the thing we probably need. You mean the actual the feature, the context feature?
Yeah.
Yeah, the from context director that we introduced in Apollo Federation.
Yeah, because if we define an algorithm, and this is, it doesn't matter what algorithm it is, if we generate the paths together with the query planning, or if we do a BFS, a DFS in the end, however we want to describe it, what the list of nodes, the list of options that we have.
Yeah.
So that's a source schema in this specification. So the list of options that we have, what is this tied to? Is this tied to a type or to the whole path?
To the whole path.
Yeah, so I can explain more about like where that comes from and how you would derive the state in the generic case of a generic implementation of federation, right? So you can imagine that after you do a path, at that point in time, you can think about for query planning remaining fields after that path. You depend on prior information in the path you're at to some extent, right? And in most cases, for if you just have a simple version of federation that just has like, requires or whatnot, you only really depend on the tail node. You don't really depend on previous information of the path. You really just care about the tail node you're at, which in that case is usually just the subgraph and the type, if that makes sense.
Yeah.
It's possible you could care about previous information in the path. That happens with from context, and so that's why we have to add a little extra stuff to the state. But that's essentially how you derive what the state should be conceptually, is by thinking about what information from the path do you really need to keep track of in order to continue query planning further beyond that path.
Okay. Okay. So, okay. And we would stop. Let's say we do this. Now we visit A, we see that we can go to B, C. Now we are on C on source schema A. The options that we have essentially is either stay on source schema E and resolve source schema A and resolve DEF, or it could be that for DEF we have to do a move to a different source schema, right? Like
Okay.
so we are now in the visitation step is we are ABC, we are on source schema A. So what we keep track of is we keep track of the source schema. We are
But it's a little different, I think, because you're not on source schema A, you're on like type C, and as part of the state you keep, you might have one or more options that specify being in one or more subgraphs.
Right.
Like because the graph we're traversing is the public API,
right.
and the state we're keeping track of as part of that is tied to the subgraphs.
But it
But
could
that's
be
not the graph we're traversing directly.
it could be that we are on source A and source B at the same time.
Exactly. Yeah.
I see.
Right. It depends
Because
on which one you took to get there. Yeah.
ABC exists on both schemas, therefore we are on both schemas at the same time. Okay.
Yeah. Basically, there's a bunch of different possibilities you can use to execute the open partial or the partial path or open path ABC. At the end of that, you could be in source A, but could also be in source B. You don't know. But those are basically described as the set of possibilities you have or the set of options you have at that point in time. And then you can query plan further from each of those sources, basically. But
Yeah.
yeah.
And then it can actually turn out that you might be able to get like field A only from source A and field D only from source B, and like you can get E and F from both.
But what would
So
happen?
then the number of options shrinks for those path extensions.
So
Yeah, like-
we agree, like in this example, the next thing that would happen is we would have to validate ABCD, ABCD E, and ABCF. So that's a selection set that is possible on type C. That's the fields of the type C. Let's remove A for now. So these are the next segments that we have to check. So we are now in this path, and now essentially this is like it's completely pseudocode, of course, but that's essentially a for each on the fields, right? So for each field, we have to verify that they are resolvable themselves. And what so let's say the condition, so if D only exists on source A, then we can say that this path would be resolvable. So we have a recursive function, of course, but that would be resolvable. And
Yeah, as long as there's at least one option at that point.
the option would be, I mean, we are on we know that like we visit the public path on the public schema, which is ABC. Now we have the possibility we could be in source schema A, we could be in source schema B. So if we are in source schema A, we can resolve D from the source schema A. That's no problem. If E is in source schema B, then that's also fine because we are already also in the path source B. Now, what happens if in this case, is this now the next visitation?
That depends on whether we have a way of getting from source A and or source B to source C. If there is there's an edge.
That's now where the edges come into play, right? What Camille said with the graph algorithm that they use, right?
Well, I mean there are different types of edges. Like basically every field is also an edge, but there are these. What do we call them? Traversals, or what position do we like the ones
Yeah,
that keep track of the conditions that they need for keys and
Yeah. So basically, each of the edges can potentially have a quote unquote condition, and the condition is something you need to sort of resolve as part of taking the edge. Or the edge is conditioned on that you can actually fetch the data you need for that edge.
But some edges are sort of within subgraph, and some edges like cross
cross
subgraph
subgraph.
boundaries, right?
That's
Okay.
right. That's right.
Yeah.
Yeah.
Okay. So conceptually, what do we do in this case? Do we now check if there's a way to traverse from source schema A to source C over an edge?
Yeah, you'll want to consider like cross subgraph edges as well through all this process, right? Whenever you can jump to another subgraph, it basically opens up another possibility for another source to be added to the list. If that makes sense.
Yeah, I guess one point here to add is like, I don't know, in my, like, if I conceptualize this, like how, I see it in my brain, let's say, it's like for every path that you already had, you just move forward until you can't, right? So, and then if you have like a long list, you try to, and that's one of the optimization, but it could be, I guess, included in the algorithm, is to find, like, if you have like, I don't know, 10 paths to get to the same place, really, you can just cut them off, prematurely. I mean, not prematurely, but cut them off if you already have a shorter path to that specific subgraph, I guess. You could like eliminate those, and then you have like fewer options and so on and so on and so on, right?
Yeah, I think it depends on, like, shorter isn't necessarily faster. So there might be different sort of
but
weights
like,
associated with
But that's
different
already
paths.
execution semantic, right? I mean,
Yeah, so that's why I think it's probably not the right place to sort of prune the options.
I mean,
At
yeah,
least not in the algorithm.
yeah, but like you could have like a lot of options purely for this, like from the satisfiability perspective.
Yeah.
And then if we like, they grow, right, over time, and then they are eliminated when there's a dead end, right? But like, if there's a path to somewhere, and and you have like, let's say, two paths that leads to pretty much the same node, which is like, I don't know, F at C on C and at subgraph A, let's say, then you don't really have to like, have two paths to get there, because you're already there. So you know that you have an access to the C at certain point, right? So you could like get rid of them and just move on, and then you have like less things to actually, check when we go deeper and deeper.
Yeah, I think the question is if we only want this algorithm for composition, or also want it to be sort of reusable for query planning. Like, do we only care about the fact that there's at least one?
We
path?
do. In query planning, there's a reason why like in composition, you just care there's at least one path, but you don't care about which path it is. And you don't really care about picking the optimal path. You just need to prove that there's at least one for each possibility, right? In query planning, you actually do care about picking the optimal path. So it's definitely different. Like there's parts of the algorithm that are reused, but there's definitely parts that are that are different.
For query planning, this is a whole different topic, and
Yeah.
something where we have to be careful as well that the spec doesn't limit us in flexibility, right? Because
Right.
we shouldn't I mean, Shane, I believe, said this last time. It's like a schema is deemed satisfiable if all of the queries are executable. All of the possible queries on the public schema are executable. Now, from an execution perspective, we should probably define execution behavior, but we shouldn't like have hard rules like you have to execute the optimal query, because in a lot of cases, this is something that or in a few cases, this is probably not even what the API should do. Like you find a path, execute the query. Like as long as it's executable, execution should be fine, right?
Right. We don't care that it's optimal. We just care that there exists at least some way to execute it. We don't really care about the specifics of it.
Yeah. There it becomes, I believe, from the execution point of view, like provides and requirements and all of these kind of things have a different a different specification from here, because I mean we don't talk about requires at the moment, but I believe you probably also have, as soon as you run into a requirement, have to check if this requirement is satisfiable from the position you're in at the moment, right? So
that's right.
It also might be that the algorithms both might be simpler if we specify them separately. I mean, if they at the end completely align, then we can do one. But I think from an understanding standpoint, it's easier if we split them.
It's also, if you know that the schema is satisfiable, execution doesn't have to build the whole graph. Execution can actually just look from where it's at and then backtrack, right? You don't have to have the knowledge of everything at this.
It depends on how you define like optimality.
Yeah, that's a big topic that we have to discuss in execution. Like,
Well, but I think that's probably something that we don't specify because
Exactly, yeah.
it's very implementation dependent.
That's exactly why I said this is a topic that we have to discuss there, because you may not want to have the optimal query plan. You may
Yeah, and there could be thousands of things that people come up with, like introducing cost, for instance, like a manually geared cost or whatever. It could also be
indexing and
yeah, it's good. Optimal execution could also mean using less resources, not necessarily being the fastest. And that is like an implementation detail that each implementation has to choose.
yeah. So from this point of view, when we're now at the path ABC, and we know that the next step that we have to take is F, and for F we know that F is on source schema C. So we now have to figure out if we can actually transition from either source schema A or source schema B to source schema C, right?
Yeah.
This would happen as part of this algorithm. We would check if there's a lookup, if we have access to the fields in the lookup to transition to this.
Yeah, but we probably want to describe it in more
Like you could just say
specific
query plan.
terms. Yeah. So we
You could-
wouldn't want to specify at this point, like actually looking at the schema and seeing if there's a lookup. Like we probably want to define, as Camille was saying, like we have a graph already here, a graph representation. We're defining the algorithm on top of something that we call a query graph. We can come up with another name, but it's something that's derived from the SDL, but it's not the schema itself.
Yeah.
To be clear, you can also define this very generically. Like you could just say, do query plan again for ABCF, and then some implementations can choose to optimize by saying, hey, I've already done ABC. Right? Because it's like essentially the same thing we did for like when we planned ABC, we got then the end ABB. You could do the exact same thing for ABCF and see what sources come out, right? And that way you don't have to talk about like the specifics of lookup or really anything. If that makes sense.
But
So-
we do need to know if there's an edge, right? And what conditions are on that edge.
Right,
So-
but that's part of query planning. Like as part of saying like telling you like the output for query planning of ABCF, what things could you be at? You could just look at that, right? If that makes
Right.
sense.
I see your point. So what you would do now is you would essentially say plan A, B, C, F, and the output of this function would be you could end up in nothing, or you could end up in that wouldn't be satisfiable. You could end up in source schema C, or you could end up in source schema D and source schema C.
That's right. That's right. And that way you don't have to like reference like how planning works or any of that. You just have to just know what sources you could be at by the end of it.
Right. So you actually need a function. So we would have to define a function. This can also be an abstract one, where we essentially say that for this specific path, give me all the source schemas that you can be at.
Or more abstractly, give me all the options at this point.
Yeah, because again, the
Although-
fact that the subgraph right now is very dependent on the features supported by Federation. That could be tweaked, but so that's maybe there's some benefit in considering them as options as opposed to a set of source subgraphs or source schema names. But yeah.
Yeah. And we don't need any context other than the path, because the planning of the options essentially would always assume query planning from the root, right?
That's
Yeah.
That's right. That's right. You don't actually need to have the path information outputted by this thing here, not for the purposes of this algorithm, at least. You
I
just
mean,
need.
the visitation itself needs to have the graph, right? So while we walk through the public schema, we build a path. We start
Yeah.
with query field A, then we give this to plan options, and it tells us that it can be in source schema C and D, source schema A and B. And then we check what fields are on the type A. Let's make it easy. Field A is type A, field B is type B, and so on. We check what fields are on type type A, and then from there on, we essentially say plan the fields of type A. And this is essentially recursively stepping through. I have this path, plan the path. We have now these schemas, and then go further and drill into. So the satisfiability algorithm itself tracks the paths and the possible subgraph it can stay on, and use
Or the options.
the
Yeah.
options. Sorry, that's gonna take at least 2 meetings for me to get this. But the options so it keeps track of the options and the path and uses the plan options, which is aligned with the query planner, to get the next option, the options for a certain path, the next path, so to say. Okay.
That's right.
Yeah.
Okay. Let's that would be
I think there's a loop in there.
yeah, I'm on it. I'm on it. So this is the schema that we are currently looking at. So the first step of the algorithm would be plan options on I mean, the first step would be the query type, but we plan just on A. And we get out that this can be source schema option. It can be option source A or source B. Then the next step is essentially recursively that we would say we plan AB and get something out of it, which could be again source A and source B. This like this, and then at some point we end up in a leaf field. That would be D. When we are in a leaf field, then we actually, do we still need to do the option planning? We do.
You
And
need
then
to make sure there's at least one, right?
it could be that it's just one, but we stop in case of a leaf field. Now, that's one condition for us to stop. The next condition for us to stop is when we are in a loop. So let's add a loop to it. So let's say from C, we can go back to A. So therefore, we have plan C and then D. Now the recursive algorithm goes further, and we say that we can go back to A. And here we would get out probably the same options.
Right. So in this case, what would happen is you've noticed you visited type A before, and when you visited type A before, you had source A, source B, and source A, source B is equal to slash a subset of the options that you generated just now, and so that means you can stop.
Because the set of options is the same. Okay. Okay. we're still missing the type information that we somehow need to track. So
Y-
here we need to know that we are on the query type. And here we need to know that we are on A.
Yeah, but to be clear, for like that first line of query plan options A, like source A, source B. Source A, source B are registered for type A, or the return type of the field that you're on, or basically like the end of the path or the tail of the path, right? Just to be clear. So
Sorry, I didn't get it.
so,
Again.
so for plan options A, source B, when you're registering a visit, quote unquote, you would store that list that you store that visit for the tail of the path, the tail type of the path, right? So in this case, the path is A, query A really. The tail type of that is just capital A, right? And so you'd register the visit is occurring for type A, and that when you've had that visit, you found options source A and source B.
Right. And it doesn't matter from where you get this.
Right. Because it doesn't matter whether you're in the middle of it or you've already done it. The point is you've already sort of processed that before. So you don't need to go through it again, is the story. Like
Yeah, but it could be that we are on a completely, so let's say many steps in the future, 142. We do plan options.
Yep.
And we do, I don't know, Q, Y, C, whatever. And from here we go to A. And if the output again is the type A with source schema A and B, we don't care because we have already visited this with the same condition. So you actually don't care about from where you come from. It's really just the tail type, as you have said it, and the set of possible source schemas. If this would end up being it's only A would be possible, you're muted, Martin.
Oh, sorry. I just wanted to say that depends on the federation features you support, right? So for us, from context, we do care about the rest of the path potentially.
Well, certain information about the path, I should say, not the entire path in the case
Yeah.
of, yeah, that's right. This is specialized right now using certain assumptions about the features that are implemented in Federation, and options may look different if you have different features.
Is this just context, or does stuff like
Provides is also handled in a very specific way in Federation. Currently, that might change in the future, but provides basically is also playing into this a little bit.
But could you still define this in terms of like a subset being a subset of the options, for instance? Like whether
Yeah, I
you
mean,
have sort of the
right.
same context somewhere in your path? Is that this?
That's right. We still use the concept of subsetting of options, and this notion of like you have less options or like the same options or a strictly smaller subset. That still exists even if you have a different set of federation features. It's just what an option consists of and whether that information, like what constitutes an option's data structure wise, is dependent on the federation features. The notion of subsetting and supersetting and all that still remains the same.
Okay.
The case of provides and external is this just part of the plan options? Like if we say that plan option essentially does a query planning for this specific path. So if a field is available only in one source schema because of provides, like the path says this field is available in source schema A only if we go through this path. We just have source schema A and source schema B as the options which come out of the plan option step. But if this specific path doesn't provide this value, then it will just be source schema B, for example.
Right. So in in Federation, we do a very specific assumption, which is that provides is treated as purely an optimization. And the result of that assumption in Apollo Federation, at least, is that we don't consider provides when it comes to satisfiability. It should be the case that even if you didn't have any of your provide statement at all, it should still be a satisfiable schema. And that's the assumption we make for Apollo Federation. That assumption doesn't need to be made, to be clear, for satisfiability to work, but you would need to change how you define your options in that case to accommodate that. So in this case, what would happen is you probably need some notion of a provide ID, or in this case, query graph nodes, maybe, if more practically speaking. But you could do that instead of having the source a comma a, like the type slash subgraph schema, if that makes sense.
So you completely ignore provides and satisfiability.
That's right. For
Oh,
sake of provide, we say that provides is purely providing a faster way to do something. So even if you didn't have your provides, you should still be able to satisfy your all your possible queries you can make.
Yeah. And I think that sort of follows from how we validate provides, right? Like the fields need to be external and external fields need to be defined in another subgraph.
yes.
Yeah. This basically makes it easy to remove what provides too, if you want, because basically it should still be satisfiable afterwards. So it ensures that like you can't really depend solely on provides to like it can't be like a load bearing provides where it sort of is necessary for your stuff to work. So that's sort of the other slight benefit of that approach. But that is the approach that Apollo takes today, at least.
There is no way that you can end up in a situation where the query would be satisfiable with the provides, where it like provides, I believe provides over entities is probably simpler, but on data, is there no case where provides could make a query actually work, and when you remove it, it couldn't work? Because, for example, the move from one source to the other source is not possible. So the only way to get this field is actually through this path through provides. Is that not an option, or does this just not work in Federation?
Right. So it provides more options for you to be able to do a thing. When we do our satisfiability planning, we assume provides doesn't exist. So it just happens to be the case that at runtime, regardless of whether your provides is there or not, we should be able to plan a query, right? Like provides gives you more options, so you could potentially be able to plan more queries. But the truth, because we in satisfiability and Apollo at least, we always make sure that it works without provides. You don't need provides at runtime. It never becomes a necessity.
Okay, so that's a big thing that we probably also, if we do it this way, I mean, these cases are very complicated to make up on the spot, but
Yeah, but Pascal, we are doing the same thing in Fusion, right? It's like a shortcut. If you have this shortcut, you can take it, but it's not necessary. Like you could just switch it off.
yeah,
It's
I mean,
just it just keeps you from doing a hop in some cases.
yeah, I agree. I mean, the only case where this could be the case is when you have, but then it doesn't make sense. Like my thing was that it could be that a value type, as you called it in Fed one, like just let's call it point with XYZ, that you can actually get the point through one specific path, and this value type is actually satisfiable. But it would actually only make sense if all of the fields are also marked as external, and therefore you can also just add the type to your graph, and then the problem is solved as well. Yeah. Okay. So one big
Yeah,
thing.
I think also it would lead to anti-patterns in designing the schema if the only way to make it satisfiable is through provides.
That's right. It makes things a lot more complicated mentally for a user to have to consider if they can only use certain paths to get to places. Like trying to debug satisfiability becomes a lot harder if you have to use provides to do things because they become chained and then it could be complicated pretty fast. So um
Okay. And what about requirements? Do you this is part of plan options, right?
Yes.
that's right.
If you cannot satisfy a requirement, plan options would just be empty, and then you have a satisfiability.
Yes, also keys could have a requirement.
That's right.
And then you cannot define if you actually can get the key because like maybe you have the key in context, but the key actually has a requirement. And that means you have to see if you can fulfill this requirement in this context.
That's right. Plan options allows us to abstract all that away so we don't have to like depend on the specifics of those semantics. It's up to sort of however that gets implemented there. So
Okay. Now the question is, what do we do with plan options?
We'll leave that as an exercise for the reader.
Plan options. is specified as gets
Small note. Here are your tasks.
done. Done. Okay. Okay. I mean, partially, I believe with this information, it's already a bit specifiable. Like, because essentially we have the walker, the DFS, BFS, whatever we want, which walks through all the possibilities, uses plan option to get the next possible set of options. And we have to, the only thing that we have to define is how we track. This is essentially just a map of a type of a list.
Yeah, there's one other thing maybe worth noting, which is how our options interpretation can be simplified, which is that it's around the behavior on type explosion today, right? So right now, when you're doing the satisfiability, when iterating through paths, Apollo basically has it so that when you encounter an inline fragment as a possibility, you can only downcast or type condition to an object type, right? We don't consider, they can technically typecast in GraphQL to anything that has an intersection of at least size 1 with possible types, but we only consider type conditions to that are object types. And that's because in Apollo Federation, at least in query planning, there's this notion of type explosion that you can do at any point in time or that you can always do. So you don't have to consider that as a possibility. That allows us to make it so there's only such that the output of plan options is really just a list of subgraphs. If you didn't have that and you try to do something where satisfiability actually looked over every possible type, then you might actually end up having simultaneous paths you have to traverse at once for type explosion. That becomes more complicated.
Yeah. How does interface object fit into this?
Well, how does interface object? That's all the complex questions. Interface object doesn't necessarily fit into this without too much issue, I would say. Like you still have the notion of like types are on it. Interface object you can think of sort of creating these virtual types to some extent, or it's sort of a shorthand notation. So you have it so that you can be of the type I, but you could also like potentially select fields that are sort of implemented by I. So it's kind of I should double check how it looks in the current code. It might actually.
But would we treat that basically as sort of the set of all possible types in that case?
We should, but I'm not 100% sure how it's treated in the code today. This is
Right.
one of those things where I have to look at the code because the current implementation of interface objects is a little tricky to understand in a lot of places, let's say.
I think if I understood interface objects correctly, the name of interface objects is also a bit difficult.
It's like a base
Oh,
type more.
It's a type,
But let's not get there because in version 1 we don't.
because if you have an interface object and then you essentially the resolver of the field that you add to the interface is on one subgraph, right? It's not like
yeah,
you
like
define an extension of an interface, so to say, that can be handled for all of the types that implement this interface.
That's
right. So
that's one use, yeah. But the other one is simply like to avoid a subgraph from having to know about all possible types that implement an interface, and just treat that as sort of a black box, as a sort of an any type.
Yeah, but essentially what you do is you add fields to all possible types.
Or you return it, for instance. I mean, that's another use for interface object. Like it allows you to return sort of any.
That's a lot like you're designing a base class or base type.
It is
And
in
then
a
you're
sense,
inheriting is like
it's
from a
much
model
more-
you. Yeah, sorry.
It's more like an existential type in languages like Swift, for instance, and I think Kotlin also has that.
Is it comparable to how's the thing called in to a trait?
Not really, because partly, but it also allows you to basically say this is sort of any, for instance, any product when product is an interface, and it allows you to like return any product without knowing about all the possible types that implement product.
yeah.
So it avoids a situation where, for instance, if you have a reviews service and a review can be defined on any product, but we have like a dozen different implementing types for a product. You don't want your review service to have to know about all those different types. It can just treat product as a type in itself.
But you wouldn't. So the review service could have a field which returns the product.
Yeah.
Right. But then that means that the interface object also has to define the key field so that you can exit from there, right?
Yeah, yeah. An interface object needs to define at least one key. And that actually needs to be sort of shared among all the
Yes,
implementations of that
that makes
interface.
sense, because then when you return it, you know that you have the knowledge about moving away. Okay.
Yeah.
Okay. But the idea, like why I say trait, is because essentially you have an interface somewhere, and then you implement like the trait for this interface. Like you say that I have a field reviews, which is on all possible products without knowing all of the specific implementations. It could be a book, it could be a movie, but
Yeah.
it will implement product. Therefore, I can somehow add a field to all of the implementations there.
But that's only one part of it, right? The other part is just being able to return like a product. So I can have like a top level query field that returns a list of products that have like very highly rated reviews. And I can return those products without knowing anything about the specific product types.
Okay. But that, therefore, okay. That's very important for the execution to know. For the satisfiability, this shouldn't matter, because if we are in a path where the paths are only on object types, right? So therefore, the reviews field that we have added to all possible products is part of this object type, and therefore plan options will tell us that we have to go to the review, or one option, at least one option will be the reviews service, right?
So paths can potentially pass through interfaces, right? So if a field returns an interface and you pass through that field, you're going to be an interface, an example, right? So, but interface objects do not matter for satisfiability, because basically they're internal to they're internal to plan options, right? Plan options is the thing that considers the fact that actually some interfaces are really objects in certain subgraphs, and by the end of it, you don't really have to get it. You just get a type, which is the type of the tail type, and then you have a bunch of sources, which are the sources that you're at. So, if that makes sense.
Yeah, why does the interface matter here? Because you said, like, why do interfaces matter at all? Because isn't this part of the satisfiability, the root algorithm, that if I'm on a field where it could be an interface, give me all possible type, and now do the planning for all possible types.
Right. I guess that's why you might say the field can pass through an interface. Like if you have a field that returns some type foo and foo is an interface, so returns product, let's say. Essentially you'll have to look at the fields on product, but then you'll also have to like type condition to each of the instances of product when you're generating the paths, and that's about it. But like if you happen to go through the interface object in that process internally to plan options, you don't really see that bubble up in satisfiability.
But just to get this straight, that means like the paths here, they don't have the type information, which is wrong. So we should actually write them correctly. So that would be, we have a query, and then we are essentially on query.
Yeah.
On query, where we have field A, where we are on A, and then we have field B, where we are on B, and so on and so forth. Sorry, that's wrong. Very hefty. So that's essentially the path that we would pass in here. Now, if this is an interface, you would essentially just have two type conditions wrapped in each other, right? So it could be that we are in the I interface, on A, and then as another option would be on B, because the interface could be implemented in both object types, right?
But I think the question is, do we need to keep track of those interfaces, or do we just keep track of like the possible types at that point, which might be like further restricted by the nested type condition.
Well, it depends on, I believe it depends on this. Is this the same thing? It is, right?
I think we may need to use our expression language to make this easier to read, like with
Yeah, that makes sense. Then we can
the
also,
angle brackets, yeah, and the path syntax with dots.
We had time, by the way.
I can't remember it now. I need to read up. Yeah, but I agree. Then we can simplify this path syntax.
It makes it a lot easier to read.
Yeah, it does indeed. Now, just one question about the one last question, then we can conclude the meeting. The information that we track, where we say we are on A and we have these options, and we are on, or we visited the type A with these options. Is the map, the context data that we store there essentially that we have type A, and then we have a set of options, and only if we have an exact match or a subset, as an exact match or a superset of any of the sets, then we can stop.
That's right. That's right.
Okay. Okay. It's a set of sets.
It is a set of sets where each set represents options. Or it represents a visit, I suppose, a visit's options. But each entry in that is a visit. And they're deduplicated because it's a set. But yeah.
Okay. Very interesting stuff. Very interesting. Okay. I mean, we're a step closer, I believe.
Yeah, we're getting somewhere.
Yeah, let's see.
I really wonder how the AI will summarize this.
You know,
So it will. So we will.
Go ahead.
Go ahead, Pascal.
What I expect the AI to do is that we have now talked about it, and I go to the AI summary, and we have the whole specification written as it should be. That's
No, and so we have to edit it. So what we have, like in the board meetings, it's usable, but it's not usable without human editing afterwards. Like it is kind of a rough summary, but it's in some way usable. Just we need to compress it and give a bit more context. So I will see. Benji will send them over to me, and I can put them in the chat when we have them. I probably just will go through and edit a bit, and then we can publish it in the repository.
okay.
Which I think is a good, like sometimes it's good to have just a reminder on some discussion points. So let's see if it's usable.
Yeah, and we'll keep track of what we have discussed in this file. Then we can have a look. If I have time, I can start writing like a rough outline of the algorithm, how it should look like. But then
Awesome.
need to see if it's already enough to get going. Okay, cool.
Bye.
Thanks a lot.
All
See you
right.
guys next week.
See you next week.
Bye-bye.